In this section, we're just going to take a look at how we do a partial fraction decomposition, not actually evaluate any integrals that contain the rational expressions. A partial fraction decomposition, and first of all, let me kind of go through what we're kind of trying to achieve with this. Generally, and you might remember this from pre-calculus, if you have something like 2 over x plus 3 plus 3 over x plus 1, what you would do is you get a common denominator of x plus 3x plus 1. And then you would just multiply the numerator by whatever's missing. And then finally, you would just combine this into one fraction. You would distribute 5x plus 11. By distributing the 2, you get 2x and 2, and then 3x and 9. And then the denominator would be x plus 3x plus 1. All right. So to go from here to here is addition of the fractions. To go this way is decomposition. All right. And that's what we're trying to do, is we're trying to go through and maybe go backwards, because if you throw an integral sign in front of this, we don't know how to evaluate something of that nature. But we know how to evaluate integrals like that. Those just become logarithms. And so that's what we're looking at in this section, is how do we go through and take something that looks like this, and we go backward into the original summons, or each of the smaller fractions that comprise that. Okay, so now to be able to do that, what we really need to do is we need to make sure that we understand the process and the setups for these. And really what it's dependent upon is it's really dependent upon what types of fractions and what types of factors that we have when we try to decompose this. All right, so there's first of all 4 types of decompositions that we're going to have to look at. The first of which is going to be the linear distinct factors. That's really easy. All right, and so if we can go through and find that they're linear and distinct, then all we're going to do is we're just going to break them up into this sort of fashion. Okay, so notice that these are all linear factors, and we're going to have a over x plus 1, b over 2x plus 5, c over 3x or 3 minus x. All right. If for some reason you have repeated linear factors, so in other words, what's inside the parentheses is a linear term, and think of this x cubed as x minus 0 cubed. So technically, it really is a repeated linear factor of x. Then what you would do is you would do the exact same thing, but for each of the different powers, you would have to go through and have its own partial fraction, right? And by the way, the letters that are up there, we're going to solve for those letters at some point, okay? These are called the undetermined coefficients, all right? And you'll be hearing me say that a lot throughout the videos. Unfortunately, if we have quadratic factors, instead of using a, b, and c, we're going to have to use ax plus b and cx plus d for each of the unique quadratic factors. And then if we have a quadratic repeated, similar to linear repeated, each power, so notice we have 3 powers, is going to have its own partial fraction. All right, so usually when you start getting into the quadratics, that's when it gets a little bit tougher. Okay, so what I'm going to do just in this video is I'm going to illustrate a fairly basic example of how to do a decomposition, and then in the next video I'll look at one that has some quadratic factors in it. So we have this x plus 7 over x squared plus 3x plus 2, and we just want to decompose this. So the first thing I'm going to do is I'm going to factor the denominator. And when we factor that out, that's going to be x plus 2, x plus 1. All right, that's pretty easy. Then I need to decide which of the 4 cases I have. All right, and sometimes it's a mix of those. But in this case, this is linear and this is linear. And clearly they're not the same, so they're distinct. So what we end up with is we have a case 1. And what I'm going to do is I'm going to break this up into a over x plus 2 plus b over x plus 1. Now here comes the algebra part of this. We need to solve for a and b. And so to do so, what I'm going to do is I'm going to clear out the fractions by multiplying both sides by x plus 2, x plus 1. So I'm going to multiply this by x plus 2, x plus 1. I'm going to multiply this fraction by x plus 2, x plus 1. And then I'm going to multiply b by x plus 2, x plus 1. And that looks like it's going to be ugly, but in fact, it actually simplifies things really nicely. This is going to cancel out, and I'm left with x plus 7. Over here, x plus 2s are going to cancel out, and I'm left with a, x plus 1. And then finally, the x plus 1s are going to cancel, and I'm going to be left with b, x plus 2. Now, what I can do is I can try to solve for a and b in a couple different ways. Okay, one way is to create a system and match the powers of x on the right side with the powers of x on the left side. All right, so, and that's the way I'm going to do it in this video. In the next one, I'm going to use a different method. All right, so distributing the x, or the a and the b, excuse me, we get ax plus a plus bx plus 2b. And now on the left-hand side, the coefficients of x, these two, a plus b, have to add up to the coefficient of x that's on the left-hand side. And so what we could do is, or another way to think about this is if we factored it, we could factor an x out, and we could have a plus b. And then over here, we just have an a plus 2b. All right, those are the leftover terms. And so the coefficient of x has to match up to the coefficient of x. So one equation that would be in our system would be that a plus b is equal to 1. All right, so again, coefficient of x, which in this case is 1, has to be equal to the coefficient of x. Then the other equation, we have 7 and we have a plus 2b. So the constant has to be equal to the constant. Okay, so that's the method that we can employ with this, is we could just go ahead and use our undetermined coefficients. All right, now we have a system. I'm going to multiply the first equation by -1. So negative a minus b equals -1. A plus 2b equals 7. We can add these together and get that b equals 6. The other thing we would do is we would just back substitute, because we know that a plus b is 1. So, and we know that b is 6. So that means that a is -5. So those are our two undetermined coefficients. And we go all the way back to the beginning, and we remember that this was the breakup. In other words, these were going to be the partial fractions, a over x plus 2, but we know that a is -5. And so what we would say is that x plus 7 over x plus 2, x plus 1, or the original value, x plus 7 over, or the original fraction, which was x plus 7 over x squared plus 3x plus 2, is equal to -5 over x plus 2. All right, so I'm just back substituting here. And then remember, we got b was 6, and the other fraction was x plus 1. Of course, if you don't trust the answer, you can always add these together to check. So add to check. All right, so somewhere in there it says add to check. Sorry about that. Let me try one more time, although you get the idea at this point. So add to check these. All right, and so that's the decomposition method. Okay, now in the next video, I'm going to take a look at one that's a lot more difficult because it's going to have a quadratic factor. Okay, so, but this is just the elementary idea of how to go through and do the partial fraction decomposition, which is actually the majority of being able to do these problems.